we're using a sample. When we use the sample, the mean is going to stay the same, but the standard deviation is going to have a little tweak in it. So that's what we're going to have to see if we can grab a hold of. Now, in most things, that's how this works, because it is impossible to test your whole population, to look at your whole population. So if you kindly open your books to, let me see where it is. It sounds confusing in the beginning, but it's really not that bad. And some of the things will start to make sense, like when I said if your sample size was 30, that'll start to make sense here now. So if you turn to page 261, 261. If you just kind of read along with me at the top, sampling distributions. In the previous section, you studied the relationship between the mean of a population and the values of a random variable. Everything was based on your population. We took this from your population. We were able to find the percentages from your population. We were able to find a person at random from your population. In this section, you will study the relationship between a population mean and the means of the samples taken from that population. So, say I'm trying to reach all the gas prices in the United States, and I can't possibly ask every gas station owner, what is your price right now for unleaded, for regular unleaded? I can go to maybe do a couple different samples. And remember, our sampling goes back to, do we want stratified? Do we want a cluster? Do we want random generated? All those come into play. Everything is always done at random, and it's done a certain way. So now maybe we're sampling a little bit here, like stratified, a little bit from the north, a little bit from the south, a little bit from the west, a little bit from the northeast, and we're sampling those. We get samples in different places, and we take the means of all those samples. That's going to represent our population. So it's a little tricky doing that because we better have good samples. Our samples better be a good representation of our population. If they're not, our answers are going to be way off. Which, when people do studies, and obviously they have to keep taking all these samples, if their samples are not good representations of their population, they have to scrap everything and start again. Because that's the most important part. You have to have a good representation of your population. Sample means, if you kind of just look at that inside box to the left, I kind of like a lot of these just because it might help trigger something for you. Sample means can vary from one another and can also vary from the population mean. It might not be a good representation from your population. This type of variation is to be expected and is called a sampling error. And we'll get to sample errors when we hit the next topic. But we have to be able to take that into account somehow. Sometimes you have to take out a sample. Maybe this sample really wasn't a good representation of my population. Maybe I sampled this room, for instance. Maybe there's 20 of you here. This is my population. I'm sampling this room, getting 5 each, taking your last test score. Maybe I got the 5 highest kids. Maybe I got the 5 lowest kids. Maybe I got the 5 middle kids. Which one is a better representation of my population? The 5 middle. The 5 highest, then I'm considering everybody up here. The 5 lowest, I'm considering everybody down here. The 5 middle, probably middle of the road. I was looking for the middle, So do I kick those out? Do I count those in? Because I'm going to take, remember, the mean of all the sample means. So I took the average of all the highs, I took the average of all the lows, I took the average of all the middles. By the time I average them out, doesn't that sound like it'll work? Right? I should get there back to the middle, shouldn't I? Because I'm going to take the average mean of all the sample means. So that's why you take all these samples and you take the mean of all those sample means. So hopefully in the long run, it will kind of, so to speak, average out. Okay, distribution is the probability distribution of the sample statistics that is formed when samples of size n, they have to all be the same size, are repeatedly taken from a population. If the sample statistic is the sample mean, then the distribution is the sampling distribution of the sample means. This is the average of all the means. Every sample statistic has a sampling distribution. A little tough to get this concept. So I'm looking for this. All these samples of the same size, taken at random, they all have to be done at random from my population. I've got these samples sitting all over the place, and if you look at their Venn diagram, see how sometimes their samples overlap? How is that possible that they overlap? If I take a sample of 5, and another sample of 5, and another sample of 5, I throw you back in each time I take a sample. So I take 5 people at random. I randomized, I took a random number generator, I took 5 people. I took the averages of all your test scores. I throw you back into the population. I take another random sample of 5. Could I possibly have picked that person I picked before? Yeah. So your Venn diagrams can overlap. Your samples can overlap. So in this case, they took 5 samples, and a couple of times they took the same one to represent 2 samples. Now, what does this mean to you guys? Essentially, what it means is this. It comes down to this. When we deal with samples, and you'll be able to tell that we're dealing with the sample because we'll say n equals. That's how you'll know we're dealing with the sample. With the population, do we ever say n equals? Nope, we have the whole population. So when we're dealing with the sample, what it comes down to is this. Your mean of your sample will be the same as your mean from the population. This is important. This is how we represent sample mean. This is my population mean. Your mean from your sample will be the same, will be equal to the population mean. But, this is the key. You have this on your paper, put a little asterisk, put a big asterisk next to this. This is the difference that you have to remember. The standard deviation of the sample mean is equal to the population standard deviation divided by the square root of how many is in your sample, divided by n. So let's see what happens. I have a standard deviation of 20. I have an n of 25. That means in my sample, all my samples, they're all a size of 25. I'm going to take all these samples, take the mean of the mean. To find my standard deviation for my sample, I'm going to take my population standard deviation and divide it by the square root of n. The square root of n is the square root of 25, which is 5. This is my sample standard deviation. Did it get bigger or smaller than your population standard deviation? If my population was 20 and my sample standard deviation is 4, what happened to it? That's smaller, didn't it? So essentially, this is what happened to it. I know this is boring, guys, but this, if you don't get this, you're never going to understand the central limit theorem. Here was my curve, right? Here was my mean. Say my mean was 80, just for instance. My mean on my sample is not going to change, but my standard deviation is going to change. So instead of being every, what did we say this was, every 20 in here, now I'm going to be every 5. So it's going to force this to go up like this. It's going to force it to get closer to the mean. Doesn't a smaller standard deviation bring you closer to the mean? It had to push that whole area, that whole spread out graph, together like this. Like if you had sand, and you made a castle. You made this round sand castle. And you said, well, you know what, I want it to be a little narrower. So you came to the sides and you squished it together. Where is it going? Is it going up? Shouldn't the middle still stay the same if you came equal from both sides? So the mean still stays the same. Your mean from your population is the mean from your sample, but my standard deviation just made my curve get a little narrower. Just made us have a little closer to the mean. It kind of takes into account, like, what happens if I didn't have a good sample in there. I want to be as sure as possible. Like the next unit when we do confidence intervals, we'll see how confident we are that something happens. But for this part, this is the key to this whole thing, is that we're going to take this standard deviation and we're going to divide it by the square root of n. Hence, we're going to force ourselves to be closer to the mean. We have less wiggle room, if you will. We're going to be much more closer to the mean. It's going to push our curve up. The mean is going to stay the same, but the standard deviation is going to change. Good? This is probably the toughest concept that you're going to have to get. If you look at the bottom of page 261, it says exactly this. The mean of the sample mean is equal to the mean of your population. That we can see. Standard deviation is going to change by taking the square root of n. The standard deviation of your sampling distribution, that is sometimes called your sampling error of the mean. Now, they go through setting this up. I used to do this, but I don't anymore. I just go through theirs. Okay. Hang with me here. You write the population values 1, 3, 5, 7 on a little slip of paper, and you put it into a hat or a box. You randomly choose 2 slips of papers with replacements, because remember, you always put it back into your population, because you can choose that person again. You're going to list all the possible samples of size 2 and calculate the mean of each. From these means form the sampling distribution of your sample mean. See if you can get through this sentence. I'm going to take 2 pieces of paper. I have a 1 and a 5. I'm going to add them together. So I get 6 divided by 2. I get 3. Its mean is 3. I'm going to throw those back in. I'm going to pull out 2 more. I get a 2 and a 4. I want to get a 2 and 4. I get a 2 and a 5. I add them together. I get 7. I take the average. I get 3.5. I pull them back. Then at the end, I'm going to take all those means from those samples, and I'm going to take the average, the mean of those sample means. With me? Okay. So it's kind of a small thing so that you can kind of see that this happens. So they want us to compare our population mean, that it stays the same for your sample. Okay? If you added these together, so 4, 9, 16, and you divided 16 by 4, isn't your mean of your population 4? Isn't the mean of your population 4? Agree? Okay. Now, keep that in mind. This is your population mean. If I put this in my L1 and I did a one-pair stat, my population standard deviation would be the square root of 5, because my variance is 5. My standard deviation is the square root. Keep that in mind. So now, we're going to come down here and we're going to compare our results. Here's my table. Here's every possible thing that could happen. I make a tree. Again, I make a tree. 1, 3, 5, 7. From here, I can get 1, 3, 5, 7. I can do the same here, the same here. Shouldn't I get 16 of these guys? I should get 16, right? So don't I have 16 of these written out? Take the mean. So I have a 1 and a 1, a 1 and a 3, a 1 and a 5, a 1 and a 7, a 3 and a 1, a 3 and a 3, a 3 and a 5, a 3 and a 7, a 5 and a 1, a 5 and a 3, a 5 and a 5, a 5 and a 7. See it go through? That's your tree. A 1, a 3, a 5, a 7 when I get to the 7. See the tree? So all they do is add these up. They take the average. Okay, so we got the average of these guys. We take all the sample means, and we take the mean of those sample means. So we come down here. Further. I didn't take the means there, sample. If you look at your book, they come down here, they take the mean of their sample means. All the means still come out to be 4. They take the standard deviation. The standard deviation says take the variance, take the standard deviation, radical 5, and divide it by, how many is in my sample? 2, divided by the square root of 2. So radical 5 divided by radical 2. It forces your standard deviation to get a little bit smaller. Does this make any sense to you? This is the part I need to make sense to you. I need you to be able to understand this. It's the same difference. It's just I'm taking a bunch of those means from samples of 2 sizes, 2 slips of paper, took their averages, if you will, averaged all those things together, and said, oh, it's still 4. But the standard deviation was the only thing that changed. My standard deviation got smaller. And yeah, I can understand how my standard deviation got smaller, because my numbers used to be a lot farther apart. Weren't they 2 apart? Now sometimes aren't they 1 apart? Aren't they closer together? So shouldn't my standard deviation be closer, smaller for this sample? We agree? Can we see the difference when we put it in your L1, L2? Well, only L1 actually. Okay? I know this is a difficult concept. They do this with like 8. I'm not doing it with 8. With 2, it's easy to see. With 3 pieces of paper, you just get that much more work to it, and it comes out the exact same, but we're okay with that because we understand the 2. Okay, now, all this thing leads up to what they call the central limit theorem. This is one of the most popular theorems for probability and statistics. So if you take a look at page 263, normally I don't like to read out the book, but this, I need you to understand where this comes from. The central limit theorem forms the foundation for your inferential branch of statistics. And why did we say that happened? Why is this what we're doing? Making it, why do we call this inferential statistics? What are we making an inference about? The population, based on our samples. We can't ask the whole population. I can't ask the entire United States kids that are seniors taking or juniors taking a statistics college class. Hey, what was your grade on your last test? By the time I did that, I had the next year of kids in there already. So I sample. I take a bunch of different samples, and my samples are very important. I go back to how I learned. They always have to be random. They could be clustered. They could be stratified. They could be systematic. Maybe I go through the list of high schools, and I take every 10 high school that I look at in the United States. Maybe I look at every 50th high school, depending on how many high schools there are. Maybe I just go to the cluster and do all New York, all Iowa, all Florida. I just do clusters. But I have to follow a good sampling. I take the average of those samples, the mean of those samples. And then of those samples, I average them out. So therefore now, I make an inference about all the students taking a college level statistics class based on my samples. That's where the inferential part comes in. That's the most important part. Why would I want to do all this? Why would I drive myself crazy? It's costly, it's time consuming, I still got a lot of things to do once I have to keep making all these different samples. Why can't I just go one person for my population? Because I don't have a background on my population. This theorem describes the relationship between the sampling distributions of the sample means and the populations that the samples are taken from. There's got to be a good correlation. The central limit theorem is an important tool that provides information that you will need to use sample statistics to make an inference about your population needs. Because it's not feasible for you to ask your whole population. Okay, basically, again, it's going to come down to your mean is going to be the same. How is this going to affect you? Hopefully that you understand at least the concept. The mean is going to stay the same, but your standard deviation is going to get smaller. Here's where your n comes in. Remember we always had to say everything was normally distributed? Your population is normally distributed. Well, now we have a couple of other ways we can say this. If your sample size is greater than or equal to 30, then we can say that this automatically approximates a normal curve. If it's not, it has to say that your population is normally distributed. If it tells us that your population is normally distributed, then we know, since we're taking good samples, that our samples will be normally distributed. So this is where I mentioned it a couple of times, 30 was your cutoff. If your sample size is going to be 30 or larger, we don't have to say normally distributed. But if it's less than that, we have to say that. And we get two things that come out of this. The mean and the standard deviation. Mark this down on your chart somewhere, on your note page. This is the crux of what we're going to be doing. Mean from the sample is equal to the mean from your population. The standard deviation is going to get smaller. It's called the sampling error of the mean, because you have all these different samples and you're combining them. I know this is a tough lesson to get through and it's probably a little bit boring, but if you don't catch why we do this, the rest of this is not going to make any sense to you. So that's the part that we're looking at. And how does this affect us? All we need to do is find the mean, find the standard deviation. And you know your Z-score formulas? We're going to use the same formulas from here on in. So let's see what causes this change to happen. Cell phone bills for residents of a city have a mean of $47 and a standard deviation of $9. This is from your population. How do I know this is a statement about my population? Residents of my city. This is my residents of my city speaking here. My mean is $47 and my standard deviation, they obviously don't live in New York. Have Verizon. Because there's no way they have a mean of $47. And a standard deviation of $9. This talks about my population so far. Now, from this population, I am going to take samples. And my sample size is going to be 100. That's my N. So random samples. Notice they said more than one. So they take a sample of 100 from this city. They ask everybody what their cell phone bills are. From that sample, they take the mean of that sample. Maybe their mean is $50, and they mark it down. They throw those people back into the population. They take another sample of 50. I could ask you twice to be in my sample. They take another, of 100, and I find the mean of those. Now I have all these samples, and I take the mean of those means, the average of all of those means. So we take random samples of 100, and we want to find the mean and the standard deviation of our samples. So what is our sample mean? You can write it like this, or you can write it like this. What is our sample mean going to be? of all our samples that we just took and averaged together? What's it going to be? What's the mean of the population? 47. We saw when we did your L1, didn't we see that the mean came out the exact same? The mean of the population is equal to the mean of the sample. This is important. However, the standard deviation is going to change. We're going to take the standard deviation from our population, which is $9, and we're going to divide it by the square root of how many are in our sample. What's our sample size? 100. So it's the square root of 100. 10. So here's our standard deviation. Look at how much it shrunk. It went from 9 to 0.9. It shrunk a lot, by a factor of 10, didn't it? It shrunk by a factor of 10. Okay, so what happened to my curve? My curve used to look like this. Here was my 47. So let me just add 9 to this, 56. Let me just show you something. I do this, 9. Okay. Now, here was my population. My sample, 0.9. So let's even estimate it to 1. I'm going to be right in here. Aren't you going to be right in here? I'm not even going to be coming out that much to get 3 standard deviations now, right? I squished them all up like this. I pulled them closer to the mean. I want less variance for error here. So this is what I want you to catch. This and this. If nothing else. So you try this one. All I want you to do is find me the mean for your sample. Find me your sample mean. It uses the same information. Our population mean was 47, and our population standard deviation was 9. I want you to tell me now what your N is, what your sample mean is, and what your sample standard deviation is. What's your N? 64. What does that mean? You took 64 people per sample from this population in this city of telephone users. Okay. What's my sample mean? Still 47. And my standard deviation for my sample would be what? So it's 9 over the square root of 64. So 1 point something. 125. Okay. So it's still smaller. Now, let's see if we can make an inference about this. When my sample size was 100, this was my standard deviation. When my sample size is 64, this is my sample standard deviation. What caused that to change? Well, I divided it by, right? Because otherwise I'm still using the same population standard deviation. So my sample size matters. So what happens? The larger the sample size, good, the smaller the sample standard deviation. And doesn't that make sense? If I divide by a larger number, shouldn't I get a smaller number? Oh, 47 is going to be my mean. That, when we do this, I stick my mean in here, don't I?
Yeah.
I'm just going to use my sample. I'm going to change this formula tomorrow to look like this. Sample mean. I'm still going to put the 47 in here. And I'm going to change this tomorrow to look like this.
Okay.
We're going to still work off your z-score formula, but we're going to tweak it just a little bit. But we have to know that the mean stays the same as the population, but the standard deviation is going to change. Is that enough?